Do this MCAT biochemistry question with me. If you like the way I teach MCAT and you want to learn more with me, I just released my MCAT passage strategy and high yield content course, as well as my free Discord channel and my free study plan. You can find more information about all three of these things at the link in my bio. So this question says, which of the following fatty acids has the lowest melting point? So when we think about melting point, we want to think about how strong are the intermolecular forces that are found within these different fatty acids. And there's kind of two major characteristics that are going to play a role in which one is going to have the strongest forces within it. And the first one is going to be the size. So a molecule that has a larger size is going to have more molecules present within it, obviously, which means it's going to have stronger or more van der Waals or London dispersion forces. That's just a characteristic of size. So the larger something is, the more van der Waals forces or the stronger van der Waals forces it's going to have. And as a result, it's going to have a higher melting point, right? It's going to be more difficult to break those bonds apart. So if we were to just take that into account, we might think that the smallest molecule is going to have the lowest melting point because it's going to be the easiest to break those molecules apart since the van der Waals forces are not going to be as prominent as the larger molecule. So then we might think the answer choice is A. However, when we're thinking about fatty acids, the size and the van der Waals forces that relate to size aren't the only characteristic that matter. The other thing is that fatty acids have the ability to stack on top of each other. And when they do that, and they do that in an efficient manner, that's going to make the intermolecular forces stronger. And as a result, you're going to have a higher melting point because those bonds are going to be more difficult to break. So when we think about stacking, what factor is going to affect that? That comes into play when we think about double bonds being present or not. Now, the way this is written, this tells you there's 16 carbons present, 18 carbons present, and 20 carbons present. And then the other number that comes after the colon tells you how many double bonds are present. So 0, 1, 2, and 4. When you have double bonds present, what that does is that introduces kinks into the structure of the fatty acids. As a result of that, those fatty acids cannot stack as properly as something that has no double bonds present. So when you have double bonds present, that causes kinks to happen. There's not stacking that occurs as efficiently. As a result, the intermolecular forces get weaker, and then the boiling point or the melting point in this case is going to get lower as well. So when we think about these molecules, yes, palmitic acid has the smallest structure, but it's not by that much, right? Just a couple of carbons. Whereas arachidonic acid has twice as many double bonds as linoleic acid, 4 times as many as oleic acid, and the palmitic acid doesn't even have any double bonds, right? So as we can see, the number of double bonds in arachidonic acid plays a really large role here because that is so many more relative to any of the other ones. So even though this is the largest structure, just slightly as we can see, it has significantly more double bonds than anything else does. So as a result, it's going to have the lowest melting point. So remember, the two factors you want to take into account when thinking about melting point and boiling point and kind of the strength of the intermolecular forces within a fatty acid is the size, of course, is going to be a major one. And then the second thing is the number of double bonds. If you have a lot of double bonds present, that's going to cause there to be an